Welcome back to the Deep Dive. We're the place you come to, well, cut through the noise and get straight to the knowledge that really matters.
That's the goal.
And today, we are plunging headfirst into a topic that's it's everywhere. Artificial intelligence.
You really can't avoid it.
No, you can't. It feels like every single day there's some new update, some unexpected application. I mean, I saw an article just this morning about AI helping design, get this, more efficient toothbrushes?
Toothbrushes. Okay, that's a new one on me. But it just shows how pervasive it's become, right?
Right. It's amazing and honestly a little bit mind-bending sometimes.
It is remarkable. It's not just, in our phones or search anymore. It's optimizing logistics, healthcare, often in places we just don't see.
Absolutely. And here's the thing. This field moves so incredibly fast. Just keeping up with the terminology, it can be a real challenge, even for people deep in tech.
The jargon changes constantly. New terms pop up all the time.
Exactly. So our mission today is pretty clear. We're going to demystify just seven essential AI terms. These aren't just buzzwords, okay? They're fundamental concepts you really need to get your head around to understand where AI is right now and, maybe more importantly, where it's headed.
Right. These terms unlock the mechanics behind the headlines.
Think of this as your personal shortcut, your way to get that aha moment without digging through tons of articles. We've done the digging, looked at a stack of sources, and pulled out the key stuff for you.
I want to give you that solid vocabulary so you can see the bigger picture, with more clarity.
Yeah, I'm genuinely excited for this one. These terms are pivotal. As we go through them, I'm really curious which ones might surprise you. Which ones have you maybe heard but weren't quite sure about? Let's kick things off with one that's gaining a lot of traction.
Yeah.
Agentic AI.
Agentic AI. Yeah, this one's fascinating because it's a real shift from, let's say, traditional AI interactions.
Okay, traditional, like chatbots.
Exactly. Most of us know chatbots, right? You ask a question or give a prompt and gives you an answer, one interaction at a time.
Right.
An AI agent, though, it operates with a much higher degree of autonomy, purpose. It can reason and act independently to achieve goals, often complex, multi-step goals.
Okay. Acting independently to achieve complex goals. That's the key difference then. It's not just waiting for the next instruction.
Precisely. It's proactive, working towards a bigger objective.
So when we say reason and act, what does that look like? Is it like one big step or is it more involved? How does it decide the next move?
Oh, it's definitely not one leap. It's more of a cycle, a continuous four-stage loop, actually. Think of it like a cognitive process.
Okay, 4 stages. What are they?
First, it perceives. It gathers information from its environment, data streams, sensors, user input.
Whatever's relevant.
Perception. Second, it reasons. It processes that info, generates a plan, figures out the best next steps towards its goal.
Right, the thinking part.
Third, it acts. It executes the plan, makes decisions, sends commands.
Action. Makes sense.
And fourth, crucially, it observes. It looks at the results of its actions.
And that feeds back in.
Exactly. That observation feeds straight back into perception, so it evaluates progress, adapts its plan, and starts the loop again. Perceive, reason, act, observe, over and over.
So it's constantly learning, adjusting.
Yeah.
That's a big step up. Can you give us some, real-world examples? What kind of complex tasks are we talking about here?
Sure. The applications are pretty broad already. Think about a travel agent AI.
Okay.
Instead of you searching flights, hotels, activities manually, you give it a high-level goal.
Yeah.
Like plan a 2-week family trip to Italy in July.
Right.
The agent could then autonomously research options, compare prices, book flights, reserve hotels, maybe even draft an itinerary. And if something changes, like a flight gets canceled, it could potentially handle the rebooking too.
Wow. Okay. That saves a ton of hassle. What about in business?
Well, imagine a data analyst agent. It could monitor financial data streams constantly. Not just flag weird spikes, but then independently research why it happened, check market trends, maybe even draft a preliminary report with findings and suggestions.
So it connects the dots itself.
Yes.
Yeah.
Or in tech operations, a DevOps agent. It detects high server load. Instead of just alerting someone, it diagnoses the cause, maybe provisions more resources, applies a patch, checks if the fix worked, then alerts a human.
Okay, that ability to handle multiple steps without someone holding its hand the whole way, that's really different.
It's transformative, moving beyond single answers to managing workflows.
That orchestration, that's where it gets really impactful. And often these agents, these sophisticated ones, they're built using a specific kind of large language model, right? Which brings us neatly to number 2, large reasoning models.
Indeed. Large reasoning models, or LRMs, you could think of them as specialized LLMs, large language models. They've gone through a very particular type of fine-tuning.
Specialized how? How are they different from the LLMs most people are interacting with?
Well, standard LLMs are great at generating coherent text quickly, based on patterns they learn from massive data sets. You prompt, they respond. Reasoning models are trained to do something, well, deeper, to work through problems step by step.
Ah, like solving a puzzle.
Kind of, yeah. The focus isn't just on spitting out an answer, but on the process of getting there, the logical steps.
So it's constructing a pathway, not just retrieving info. How do you train that? What makes it reasoning focused?
The training uses problems where the answers aren't just about pattern matching. They need a sequence of logical steps to be verifiably correct.
Like math problems for code.
Exactly. Complex math proofs, coding problems you can check with a compiler, logic puzzles. Using techniques like reinforcement learning, often with human feedback, the model learns to generate the sequence of reasoning, the chain of thought that reliably leads to the right answer.
Chain of thought. I've heard that term.
It's about building that internal logic and being able to show its work, essentially, not just the final conclusion.
Okay, this connects to something I've noticed. You know when you use a chatbot, and sometimes there's that little pause, or it might even say thinking, before it gives a really detailed answer. Is that the reasoning model doing its thing? Generating that internal chain of thought?
Very often, yes.
Yes.
That pause isn't just lag. It's the reasoning model actively breaking down your query, exploring logical paths, constructing that step-by-step solution internally before it formulates the final response.
So it's actually computing the reasoning path.
Right. It's building that scaffold of thought. That's what lets it handle more complex, nuanced problems accurately. Especially important for the autonomous actions of those agentic AIs we just talked about.
That makes perfect sense. Okay, let's shift gears a bit. Let's go sort of deeper under the hood to a foundational technology, vector databases. Sounds technical, but the idea is actually quite elegant.
It really is elegant and incredibly powerful. So the core idea, a vector database, doesn't store data like you normally think of it, not the raw text file or the image as a blob.
Okay, so what does it store?
It uses something called an embedding model. That model is key. It takes raw data, text, images, audio, whatever, and transforms it.
Transforms it into what? And why bother?
It transforms it into a vector, which is basically just a long list of numbers. Think of it like coordinates for a point in a very high-dimensional space.
Numbers, representing an image or text.
Yes. And here's the magic. That list of numbers, that vector, captures the semantic meaning, the essence, the characteristics of the content.
Semantic meaning, so not just keywords.
No, much deeper. An embedding for a picture of a cat isn't just pixels. It's a numerical representation of catness fur, whiskers, maybe its relationship to pet or predator. A vector for a house cat would be numerically close to a vector for a lion, but far from a vector for, say, a bicycle. It encodes context.
Wait, so the computer can understand catness through numbers and relationships between concepts. That's pretty wild. What's the big benefit of doing all this?
The huge benefit is similarity search. It's way beyond keyword searching. In a vector database, searching is basically math, measuring the distance or the angle between these numerical vectors in that high-dimensional space.
So you're looking for vectors that are close together.
Exactly. And close in that mathematical space means semantically similar in the real world. Similar meaning, similar concept, regardless of the exact words or file type.
Okay, give me a concrete example. Let's say I have a picture of a beautiful mountain vista. What happened?
Right. You start with your mountain picture. The embedding model turns it into its unique numerical vector. Now, you do a similarity search using that vector. The database finds other vectors mathematically close to it.
Which could be other mountain pictures.
Could be, yes. But it could also be text articles about hiking or scenic views, or maybe even music files that have a similar feeling, grandeur, tranquility. The search crosses formats based on the underlying meaning, the vibe, not just keywords.
Okay, that's genuinely impressive. Understanding meaning, not just matching terms. And this ties into our next term, doesn't it? Vector databases are key for ag.
Absolutely. Or RAG, retrieval-augmented generation. It's a really crucial technique, especially in enterprise AI. And yes, it leans heavily on vector databases.
Why is it so crucial? What problem does our array solve?
It directly tackles a major challenge with LLMs. Sometimes they, well, they make things up, hallucinate, Or their knowledge is outdated because they were trained a while ago.
Right, they don't know about things that happen after their training cutoff.
Exactly. Our GAG helps fix that. It enriches the prompt you give the LLM with relevant, up-to-date information before the LLM generates its response. It makes the answers more accurate, more grounded in facts.
Okay, grounding the LLM, how does that augmentation actually work? Step by step.
It's quite neat. You give it a prompt, say a question. A component called the arg retriever takes your prompt. It uses an embedding model, just like we discussed, to turn your prompt into a vector.
Okay, the prompt becomes numbers too.
Yep. Then it uses that prompt vector to do a quick similarity search in a vector database. But this database is special. It's filled with your trusted, specific, up-to-date information. Company docs, recent reports, knowledge-based articles.
Your own curated knowledge.
Right. The system retrieves the most relevant snippets of info from that database based on your prompt's vector. And then this is the key part. It takes those relevant snippets and stuffs them into the original prompt, augmenting it before sending the whole package to the LLM.
Ah, so it's like giving the LLM a cheat sheet, a very specific, relevant cheat sheet based on my question drawn from trusted sources.
That's a great way to put it.
So if I ask about, I don't know, a specific detail in our company's current benefits policy.
Exactly. The RAG system wouldn't just rely on the LLM's general knowledge. It would fetch the relevant section from the actual employee handbook stored in the vector database, inject that text into your prompt, and then ask the LLM to answer based on that specific provided context.
Which means the answer should be accurate, up-to-date, and directly related to the company policy, not just a generic guess.
Precisely. It grounds the response in verifiable, current data, massively reduces hallucinations, makes the LLM much more trustworthy for real-world applications. It's a huge deal for practical deployment.
Incredibly useful. Makes AI much safer and more reliable for businesses. Okay, next up, Model Context Protocol, or MCP. This also sounds like it's about making LLMs more practical, but maybe less about accuracy and more about connection, integration.
Exactly right. It's all about integration and utility. Look, for LLMs to be really powerful in the real world, they can't just sit there in isolation. They need to talk to things. External data sources, services, software tools.
Right, they need access to information or the ability to do things.
Correct. But historically, getting an LLM to connect to, say, a specific database or a company's internal API required developers to build custom one-off integrations every single time.
Which sounds like a massive pain, not scalable.
Not at all. You'd be writing specific code for every single connection. MCP is designed to solve that exact problem. It standardizes how applications provide context and connect to LLMs.
A standard, so like a universal plug.
Kinda, yeah.
Yeah.
Think of an MCP server as a standardized connection point. Universal translator, maybe. It defines a common language, a common structure. So the AI knows exactly how to interact with any external system that supports MCP. No more custom code for each connection.
Okay, that sounds like a lifesaver for developers, a huge efficiency boost. What sort of systems could an LLM connect to using MCP?
Oh, a huge range. External databases, obviously, for querying or updating info. Code repositories, maybe to understand existing code or even help write new code. Email servers for processing messages or drafting replies. Calendars for scheduling. CRM systems for customer data. Even things like IoT devices.
Wow, so it opens up a massive ecosystem for the AI to interact with.
Exactly. It brings huge benefits in efficiency, scalability, security, too. It lets LLMs interact reliably with all sorts of different digital tools, making them vastly more useful across the board.
The idea of an AI orchestrating actions across different systems via one standard, that really does point towards a much more integrated future.
Okay, number 6, mixture of experts. MOE. You mentioned this idea isn't brand new.
That's right. The core concept actually dates back to a research paper from 1991. But it's only now, with today's computing power, that it's become a really, really big deal for large language models.
An old idea whose time has come. So what is it? How does it work?
Well, MOE changes the fundamental architecture. Instead of one giant monolithic model where basically all the parts are working on every task.
Right. One huge brain doing everything.
Yeah. MOE divides the LLM into a series of experts. These aren't people, obviously. They're specialized neural subnetworks, submodels, and MOE model might have dozens, even hundreds of these focused experts.
Okay, like specialized mini brains within the main model, each good at something specific. That's a good analogy. One might be great at language translation, another at coding, another at historical analysis, and so on.
Fascinating. But how does it know which expert to use for a given question? Does it activate all of them?
Ah, that's the clever part. And where the efficiency comes from. There's a routing mechanism, usually another small neural network, that looks at the incoming data, maybe even each word or token.
Token by token.
Sometimes, yes. And it dynamically decides which specific experts are needed for that specific part of the task. It routes the computation only to the relevant specialists.
So if I ask a question about history, it sends it to the history expert. And if the next part is about math, it routes to the math expert.
Pretty much, yeah. Then, once those activated experts have done their processing, there's a merge process that combines their outputs back into a single, coherent result that moves on through the model.
Okay, so it only calls up the specialists it needs right when it needs them. That sounds incredibly efficient. This is the key to scaling models without insane compute costs.
That is the absolute core breakthrough. It's a way to build models with truly enormous numbers of parameters, making them incredibly knowledgeable and capable, but without the compute cost skyrocketing proportionally during inference, during actual use.
Because you're not running the whole giant thing all the time.
Exactly. Only a fraction of the total parameters, maybe 10 or 20%, might be active for any single input. You get the benefit of a massive model's knowledge, but the operational cost is manageable. Some of the big models out now, like IBM's Granite series, use this MOE approach with dozens of experts.
So you can have vastly larger, more capable models than before because they're structured more efficiently.
Precisely. It's pushing the boundaries of LLM capabilities, enabling things that were just too expensive before.
That is a clever design. Really revolutionary. Okay, on to our seventh and final term, the big one, maybe the most speculative, ASI. Artificial Superintelligence. This is purely theoretical stuff, right?
Absolutely. ASI is, you could say, the ultimate theoretical goal for many cutting-edge AI labs. But yes, crucial point, it does not exist. It's purely hypothetical right now.
Okay. So how does it relate to AGI, Artificial General Intelligence, which people also talk about?
Right, so AGI is also theoretical. AGI would be an AI that can perform essentially any intellectual task that a human can, across any domain, at least as well as a human expert. Human-level general intelligence.
Human level across the board. Got it. So ASI is more than that. What makes it super...
ASI goes a significant step further. An ASI wouldn't just be as smart as the smartest humans. It would possess an intellectual scope and problem-solving ability profoundly beyond human intelligence, across practically all fields. Vastly smarter.
Wow.
And the really defining characteristic, the thing that makes it so potent and frankly debated, is its potential for recursive self-improvement.
Recursive self-improvement. That
Yeah.
sounds powerful. And maybe a little scary. What does that actually mean?
It means an ASI wouldn't just be super intelligent. It would be intelligent enough to understand its own design and improve it, to make itself even smarter, faster, more capable.
So it could redesign itself? Upgrade itself?
Yes. And then that smarter version could do it again, potentially leading to an accelerating cycle of ever-increasing intelligence. An intelligence explosion, some call it.
Okay, the implications of that,
Yeah.
they seem enormous.
They really are. On one hand, proponents imagine an ASI could solve humanity's biggest problems. Disease, climate change, poverty, maybe even enabling interstellar travel. Things currently beyond our grasp.
The ultimate problem solver.
But on the other hand, there are huge concerns. An entity so vastly more intelligent could have goals misaligned with ours, or could create unforeseen consequences, new problems we can't even comprehend, let alone control. Its sheer capability makes it unpredictable.
So massive potential upside, massive potential downside.
Exactly. Which is why, even though it's purely theoretical today, it's a really important concept to keep on the radar, to discuss the ethics and alignment challenges long before it potentially becomes a reality.
What an incredible journey through these terms, from, AI agents acting on their own, all the way to the theoretical potential of ASI. It really hammers home how fast this field is moving.
It truly does.
Yeah.
The landscape is constantly shifting. Staying informed is, well, it's an ongoing process, a fascinating one, but ongoing.
Absolutely. And as we wrap up this deep dive, that idea of recursive self-improvement, especially with ASI, it leaves us with a pretty big question for you, our listener, to mull over. Given that theoretical potential for AI systems to literally improve themselves, maybe exponentially, how might our own human understanding of intelligence itself need to change, need to evolve? And maybe even more critically, what new kinds of collaboration or perhaps even new modes of coexistence might humanity need to figure out, need to master to navigate a future with potentially superintelligent entities?
Yeah, that's a profound question. Definitely one that pushes us to think about the long-term horizon of all this.
Well, thank you for joining us on this deep dive into AI's evolving lexicon. We really hope this cleared things up and maybe sparked even more curiosity about where all this is heading.
Hope it was helpful.
We look forward to diving into more complex topics with you next time.